Let us discuss multiple expansion. Okay, generally, the approximate potentials at large distances. If we consider a localized charge distribution, this is the localized charge distribution, and if we are observing from the point P, or if you are looking from the point P, the potential V is equal to Q over 4 pi epsilon 0 R, where Q is the total charge of this localized charge distribution. If we look far from this localized charge distribution, we feel this as the point charge Q. Point charge having the charge Q is the total charge of this localized charge distribution. And if Q is equal to 0, the potential at this point is equal to 0. Okay. Then let us consider a point charge distribution, localized charge distribution. One negative charge is situated here and another positive charge Q is situated here. And if you are looking from another point P, this is the distance R1 and this is the distance R2. Okay, there is not much difference between the distance R1 and R2 because this point is too far from this localized charge distribution, and this localized charge distributions are too close when we are consider the distance between this charge distribution and the point P. Okay, at that time the total charge of this system is system V is equal to 0. Okay, total charge Q is equal to 0. So if Q is equal to 0, then we will get V is equal to 0. Okay, so this is approximate case. We need to consider the potential at this point P as we need to add the potential due to this point charge as well as this point charge. Then that will not be equal to 0 at this point. Okay, so if we consider this total charge is Q is equal to 0, then we can approximate the potential V is equal to 0. So we need more systematic expansion of this potentials. Okay, more systematic expansion of this potentials. Like when we need to consider the dipole case, we need to consider the quadrupole case, and etc. Okay, in that way or in that system, we are going to consider here, and we are going to expand the potential of an arbitrary localized charge distribution by using an equation V of R is equal to 1 over 4 pi epsilon 0 integral 1 over 4 pi epsilon 0 integral 1 by R rho of R d tau. This is total charge. Integral rho of R d tau is total charge Q over R. Okay, so we need to make a systematic expansion of the potential due to different system of charges like dipoles and quadrupoles and all. Okay, so here let us develop a systematic expansion for the potential of an arbitrary localized charge distribution in power of 1 by R. Okay, so here we are going to consider here we are considering a system of charges, and in specific we will consider a single point charge as well as a dipole as well as quadrupole, etc. Okay, so when we are considering the potential at the point P, we can use this relation V of R is equal to we need to add the potential due to all of the small volumes. Okay, potential due to all of the small volume charge distribution, and we need to add up to get the total potential at this point P. V of R is equal to 1 over 4 pi epsilon 0 1 over R. We need to look at this letters R here, vector R. This is the origin. This we are considering as the origin, and this is the volume charge. This is the volume charge density. This is a specific volume d tau dash, small volume d tau dash, and the distance when we are considering the charge distribution at the small volume d tau dash, the distance between the origin and that small volume is vector R dash. Okay, that is the vector, and using this relation we can add up all the potential due to small volume charge distribution at each and every point in this localized charge distribution. Okay, so using law of cosines, R square, this is R, the distance between the small volume and P is the R. R square is equal to R square. Okay, that is the magnitude of the distance between the origin This is the point we are considering origin and the point P. So r square plus r dash. R dash is the distance between the origin as well as the small volume theta dash. So r square is equal to, when we are considering this triangle, when we are considering this triangle, by using law of cosines, r square is equal to r square plus r dash square minus 2r dash cos theta dash, where theta dash is the angle between this r and this r dash vector. Okay, and r is equal to, we can write this relation as r is equal to, when we are taking the root of this equation, r is equal to under root r square. Under root r square is r into under root 1 plus r dash divided by r whole square minus 2r dash divided by r cos theta dash. Okay, for that we are considering 1 plus this term as under the root, this term as epsilon. Okay, and that epsilon is equal to r dash divided by r into r dash divided by r minus 2 cos theta dash. In that equation we are taking this r dash divided by r outside, so we can write r dash divided by r into, here we will get r dash divided by r minus this has taken outside, so 2 into cos theta dash. So that relation can be written as r is equal to r into 1 plus epsilon. Okay. So we can write this relation as r is equal to r into under root 1 plus epsilon as 1 over r is equal to 1 over r under root 1 plus epsilon. Okay, so if we take this into numerator, we can write 1 plus epsilon whole raised to negative 1 by 2. Okay, negative 1 by 2. And since this r dash is the distance between the origin and a localized volume, and this is the r is the distance between this localized charge distribution, this origin, and the point P far away from this localized charge distribution. So r is greater than r dash. R is greater than r dash. So we can write, we can use binomial expansion for this one. So that is equal to 1 over r, 1 minus 1 plus x raised to negative n is equal to 1 plus negative n into x minus, this is the relation. We can expand by using binomial expansion. For this relation, 1 plus epsilon whole raised to minus 1 by 2 is equal to 1 minus 1 by 2 epsilon minus 1 by 2 into minus 1 by 2 minus 1 over 2 factorial epsilon square, and here negative 1 by 2 into negative 1 by 2 minus 1 into negative 1 by 2 minus 2 over 3 factorial into epsilon cube plus etc. Okay, we can use that binomial expansion here, and we will get 1 over r into 1 minus 1 by 2 epsilon plus 3 by 8 epsilon square minus 5 by 16 epsilon cube plus etc. Okay, and we need to substitute the value of epsilon here. So the value of epsilon is 1 minus 1 by 2. Value of epsilon is r dash by r into r dash by r minus 2 cos theta dash plus 3 by 8 r dash by r whole square, r dash by r minus 2 cos theta dash square minus this term. Okay, and then we need to expand those terms, r dash by r minus 2 cos theta dash whole square. This is in the form of a minus b whole square, and we can expand by using the relation a minus b whole square, and here also a minus b whole cube. That by using that relation we can expand this term. And finally we need to rearrange that expansions like this as the coefficient of r dash divided by r, as the coefficient of power of r dash divided by r. Okay. So that relation can be written as, that is equal to 1 over r plus 1 plus the coefficient of r dash by r from this relations is cos theta dash, and plus r dash divided by r whole square, this is 3 cos square theta dash minus 1 over 2, and the coefficient of r dash divided by r whole cube is equal to whole cube into whole cube is 5 cos cube theta dash minus 3 cos theta dash over 2 plus etc. Okay. So here, look at this relation. The coefficients of power of r dash divided by r, coefficients of power of r dash divided by r are legendary polynomials. We know the legendary polynomials are sum over n is equal to 0 to infinity Pn of x, or here if we take instead of x cos theta dash. So if we take P1 of cos theta dash, P1 of x is equal to x. P1 of x is equal to x. That is the first coefficient. P1 of x is equal to x. P1 of cos theta dash is equal to cos theta dash. And P2 of x is equal to 3x square minus 1 over 2. 3x square minus 1 over 2. So for x here cos theta dash, that is 3 cos square theta dash minus 1 over 2. And this is 5x cube minus 3x over 2 is the third legendary polynomial P3 of x. Okay, so the coefficients of r dash divided by r is the legendary polynomial. So we can write this relation 1 over r is equal to 1 over r, sum over n is equal to 0 to infinity r dash divided by r raised to n into Pn of cos theta dash. Okay. And we know V of r is equal to 1 over 4 pi epsilon 0 1 by r rho r dash d tau dash. Okay, so we got 1 by r is equal to 1 over r, sum over n is equal to 0 to infinity r dash divided by r whole raised to n Pn cos theta, where Pn cos theta is the sum over n equal to 0 to infinity Pn cos theta is the legendary polynomials. Okay, so V of r is equal to 1 over 4 pi epsilon 0 integral instead of 1 by r we can write this term 1 over r, sum over n is equal to 0 to infinity r dash divided by r whole raised to n Pn cos theta dash rho of r dash, Pn cos theta dash and rho of r dash and d tau dash is there. Okay, so that is equal to 1 over 4 pi epsilon 0. We can take this sum outside, sum over n is equal to 0 to infinity. So here r into r raised to n is r raised to n plus 1. Here we are integrating with d tau dash, so we can write this r raised to n plus 1 outside this integral, and integral r dash raised to n Pn cos theta dash rho of r dash d tau dash. Okay, so we can expand this term more explicitly. V of r is equal to, the first term is 1 over 4 pi epsilon 0, 1 over 4 pi epsilon 0 when n is equal to 0, we will get 1 by r rho raised 1 by r integral rho of r dash d tau dash plus 1 by, if n is equal to 1 1 by r square integral r dash cos theta dash rho of r dash d tau dash plus if n is equal to 2, then 1 by r cube integral r dash raised to n r dash square 3 by 2 cos square theta dash minus 1 into rho of r dash into d tau dash plus etc. Okay, so this is the multiple expansion of potential V in power of 1 by r, Okay, look at this term 1 by r, here 1 by r square, here 1 by r cube. So first term represents, that means 1 by 4 pi epsilon 0 1 over r integral rho of r dash d tau dash, that represents for that we will get for n is equal to 0. So V is proportional to 1 by r. This term is monopole contribution. If we take this term, this is in the form of 1 by 4 pi epsilon 0 q over r. Okay, that is the monopole distribution, that is the monopole contribution. So we first told V is equal to, we are considering this as point charge, q over 4 pi epsilon 0 r. Okay, actually that's not the precise result, that is not the absolute result, that is an approximation. V is equal to q over 4 pi epsilon 0 r. So first term 1 by 4 pi epsilon 0 1 over r, this term is q, rho of r dash d tau dash is q, integral rho of r dash d tau dash is the net charge q. So we will get the first term monopole contribution 1 over 4 pi epsilon 0 1 by r rho of r dash d tau dash. Okay, and n is equal to 1, V is proportional to 1 by r square. This is the dipole contribution, 1 over r square integral r dash cos theta dash rho of r dash d tau dash is the dipole contribution. Okay, and third term is V is proportional to 1 by r cube, quadrupole contribution, and fourth term is n is equal to 3, V is proportional to 1 by r raised to 4 is the octupole contribution. So the lowest non-zero term in the expansion provides the approximate potential at large R, and the successive terms tells how to improve the approximation if greater precision is required. Okay, the lowest non-zero term, that means, for example, this is P of R is equal to 1 by 4 pi epsilon 0 1 over R, rho of R dash d rho dash. This represents monopole contribution. Okay, and if we consider a dipole, let a negative q and a positive q charge is there, then the total charge q is equal to negative q plus q is equal to 0. So that means here integral rho r dash d rho dash. So the monopole term will become 0 for this case. The lowest non-zero term will be this one. Okay, lowest non-zero term will be this one. Look at this one. The first term is proportional to 1 by r, second term is proportional to 1 by r square, and third term is proportional to 1 by r cube. If r is greater, then the successive terms will become so small. Okay, that will not contribute. That will not bring much change in the monopole term, or that will not bring much change in the lowest non-zero term. Okay, for example, if this is 1000, then this will be 10, and the third term will be 0.1. In that case, the 10 as well as 0.1 will not make that much change in the value of 1000. That means the lowest non-zero term, this one, or this one, or some other value. Okay.